Okay, so yesterday we finished off talking about alpha halogenation. We have one more really useful reaction to talk about from that section, and this is called the Haloform reaction. You guys have actually done this reaction, assuming you made it through your whole synthesis project. Let's take a look at the overall mechanism for this, and we'll try to walk our way through it because it's fairly intuitive. And I'm going to draw in 3 hydrogens coming off this end. You can assume over here we've just got 3 methyl groups, so it's a terbutyl group. And in this reaction, you treat a methyl ketone with really strong base like sodium hydroxide, and then a halogen like Br2 or Cl2 or I2, any halogen species. So what do you think will react first, the iodine or the base? The base. So we covered yesterday the fact that a base can deprotonate one of these. The equilibrium, if we think about it, is really not that favorable, so we should maybe draw it a little bit more like this. And we can, let me actually make these red arrows. We can push these electrons onto this carbon and we can form our enolate. We don't have very much of this enolate in solution, but we have just enough. And we said yesterday this carbon can act as a nucleophile and attack a halogen. So in the next step, what we can do is treat this with bromine. But like I said, you can use Cl2 or I2. And this enolate will attack our bromine and kick off a bromide. Pretty much the exact same reaction that we covered yesterday. But yesterday I made a point of saying that oftentimes this results in overhalogenation, right? Because if we think about these remaining protons coming off the methyl ketone, they're actually more acidic than the starting material, right? So oftentimes you overshoot. And so we'll do this 2 more times, I should say. And I'm not going to draw out the full mechanism, I'm just going to write times 2. And we'll get 3 bromines installed. So oftentimes when you do this reaction, you add in excess of your halogen and you use a large amount of base. When you guys did this in lab, you guys had those 800 milliliter beakers. They were huge. You added in a ton of bleach and a ton of sodium hydroxide. All right, if we've got extra sodium hydroxide, this sodium hydroxide can actually attack in to the carbonyl and kick up electrons onto this oxygen. I'm going to just abbreviate this CBr3. We've got our hydroxide that added in, and this oxygen is now an anion. The interesting thing is that this is now a decent leaving group. Why is this a decent leaving group? We normally don't kick off carbons. Yeah, let's take a look at it after we kick it off. So we've got our, actually let me draw out this bond, and then CBr3 as an anion. In this case, the anion is very stable because of all the induction, right? In your case, you guys had chlorines on there. That makes it even more stable because chlorine's more electronegative than bromine. Once you kick this off, you get a really rapid proton transfer where it will pluck off this proton from your carboxylic acid. You get O- plus HCBr3. And then in lab, you guys treated this with HCl until you got to a low pH. And that was in order to isolate your neutral carboxylic acid rather than the carboxylate salt. This was a really popular reaction in organic chemistry labs for a qualitative test. What you would do is if you thought you might have a methyl ketone as an unknown compound, you treat it with iodine and sodium hydroxide. It would do this full haloform reaction. And the interesting thing is oftentimes this product that you get out will precipitate out of solution. So if you observed a precipitate crashing out of solution, you knew you probably had some sort of methyl ketone. This really only works with methyl ketones. It won't work with an ethyl ketone, won't work with a terbutyl ketone, obviously. You have to form the trihalogenated species in order to kick off that carbon. So it's a unique reaction. But the nice thing with this is last chapter we covered a wide variety of ways to interconvert carboxylic acids into other functional groups. So now we've got a pretty useful tool. A lot of people were confused last year by this because they said, well, if you think about our lab, right, we had a methyl ketone, so we'll just use the acetophenone pathway. We treated this with bleach and sodium hydroxide, followed by acid. And we were able to get our carboxylic acid. Why did this reaction work? We don't have a Cl2 in there. Or do we? Dun, dun, dun. There we go. If you think about this in solution, if you have bleach and you've got sodium hydroxide around, you actually generate a very small amount of Cl2, and this is the active species, and that's why you had to use so much bleach, is you had to have a reasonable amount of Cl2 in order for this reaction to occur. In fact, if you add acid into bleach, you end up generating a huge amount of Cl2, and it can be poisonous. So if you're ever at home, don't mix acid and bleach. That's a terrible idea. But this is a mechanism that I do want to see in your lab report. So I want to see the full haloform reaction for your conversion of your methyl ketone into your carboxylic acid. All right, we're all done with alpha halogenation. Now we get to go into the more interesting chemistry from this chapter. The next reaction we're going to talk about is the aldol reaction. The aldol reaction looks more complicated than it is. You can use an aldehyde or a ketone. Typically you see aldehydes because aldehydes are more reactive than ketones. And if you treat this with sodium hydroxide and water, so just basic solution, what you'll observe is a good portion of your product will get converted into this new species. And this is referred to a beta hydroxy aldehyde. So if you remember yesterday, we said alpha is 1 carbon away, beta is 2 carbons away. The aldehyde is a higher priority, so we treat the OH group as a substituent. So it's beta hydroxy aldehyde. Let's try to figure out what the mechanism is for this. So we've got this aldehyde, and we're going to treat it with sodium hydroxide. What's this aldehyde called to begin with? What's the starting material called? You could call it ethanol. What was the other thing that we call it? Yeah, acetaldehyde. So if we treat this with sodium hydroxide, what do you think will happen? Deprotonate. Yeah, we said that it's not a very favorable equilibrium, but it works well enough where you will generate a small amount of enolate in solution. I'm going to draw in both of these hydrogens just for the time being. And what do you think happens if we've got more acetaldehyde around? So let's assume we've got another equivalent. I'm just going to write leftover or unreacted. What do you think could happen? Yeah, we've got a good nucleophile, we've got a good electrophile, right? So if we look at this, this is nucleophilic. This is electrophilic. And you can have your enolate attack the other unreacted aldehyde and kick up electrons onto that oxygen. Oops. All right, so now we've got our intermediate, and then we said that there's water around in this reaction. So if we've got water around, we can just protonate that alkoxide that we formed, and we can get our beta hydroxy aldehyde. And there we go. One thing I will say is aldehydes tend to form the beta hydroxy aldehyde, but ketones don't really do this reaction very well. Does anybody know why? Not resonance. Fair guess. I'll give you half credit. Yeah, ketones are less reactive. When we covered ketones and aldehydes, we said that aldehydes are much more electrophilic, which facilitates this reaction going forward. Ketones are much less electrophilic, so they're typically not as reactive. You typically favor your starting material side. So with aldehydes, you can consider the fact that most of the time you're forming a majority of that beta hydroxyaldehyde, but with ketones, you're typically stuck more at the starting material side, and you might have a trace amount of your beta hydroxy ketone. So let's make some notes about the aldol reaction. So aldols, or aldol addition, is favored with aldehydes since they are more electrophilic. Than ketones. The other interesting thing with this reaction is that the reverse reaction is also possible, meaning you can convert from your beta hydroxy aldehyde or ketone back to a ketone or an aldehyde. This is a big deal in biochemistry, and a lot of our enzymes actually facilitate that reaction. So there's actually an enzyme called aldase. Have you guys learned about that? No? Well, when you get into biochem, you're going to learn about it a lot more. We're not going to really have enough time to talk about it in this class, though, but basically it's what's called a retro-aldol reaction. So retro just means it's going backwards. So let's take a look at the mechanism for the retro-aldol.
Got a question?
Yep. Sorry.
Does it matter if you have a methyl or like ethyl substituent off the aldehyde?
No, the alpha position, the pKa is going to be roughly similar, whether or not it's a methyl ketone or an ethyl or methyl aldehyde or an ethyl aldehyde. So it will work with any aldehydes, really.
Is it always going to work on the carbon closest to the oxygen?
Yes, exactly. So the most acidic carbon is always going to be that alpha carbon, which means that carbon is going to act as the nucleophile. Yeah, that's a great question. So let's take a look at the retro-aldol. If you can do a reaction backwards, you can probably do it forward, so this is a good check. What's going on back there, guys?
They're arguing about chemistry.
As long as it's about chemistry. All right, first step in a retro-aldol is basically the arrow pushing scheme we drew before, just backwards. So we'll form a carboxylate. Oops, thank you. That should be an aldehyde. Actually, let's do a ketone just to mix it up, because we know ketones actually prefer to go in reverse. So we've got an alkoxide. And now that we've got this will look funny, but what we're going to do is clamp down and kick off an enolate. And then last but not least, we've got water around. This enolate will take a proton from water, and you'll go back to your ketone. Like we said before, the ketone really prefers to go in the reverse direction.
Does an enolate always have to react with aldehyde? Or can it react with a ketone as well?
An enolate's more likely going to react with an aldehyde because it's more electrophilic. Yeah. All right, let's take a look at some example reactions. Let's do this one. Let's say I've got this aldehyde we're going to treat this with sodium hydroxide and water. This will be a 5-point quiz problem. It's worth more. Let's try to figure out what the product looks like here. So I'll give you guys a minute to work on the mechanism for this. I'm just going to fill in a little bit of our skeleton so we can work through the mechanism faster as a group. Raise your hand if you feel pretty comfortable with the product you got. A few people? Raise your hand if you're still working on it. All right, I'll give you guys another minute. Okay.
Is that your time?
No, I wish. All right, let's try to work through the mechanism really quick. We know in the first step, acid-base chemistry tends to dominate. So we'll pluck off one of these alpha protons and form an enolate. So we've got a negative charge on this carbon. We know most of it doesn't form the enolate. We're typically left with the majority of the unreacted aldehyde. But now we've got this good nucleophile, right? we've got an electrophile over on the aldehyde that's left over, so this can attack in, kick up electrons. Okay? Got O minus, we've got H. There we go. Looks a little funky, but that's fine. The last step we said is just to treat this with water. And we can grab a proton off of water, and we can get to our final product. Where we've got our beta hydroxy aldehyde. Am I missing a carbon? Shoot. Oh, yeah. Thank you. That would have been embarrassing. I would have lost a point on that 5-point problem. All right. The easiest thing you can do when you're looking at these problems is to identify the alpha carbon on your aldehyde. All right. So we've got our alpha carbon right here. And then identify the beta carbon where the alcohol is coming off. Retrosynthetically, all we did was we made this bond, right? And then we can say that this used to be a CO double bond. So retrosynthetically, these problems really aren't that hard to work with. The key thing you have to do is identify your alpha position, the beta position where your alcohol is coming off, cleave those apart, and then convert the alcohol into a carbonyl group. So let's do an example of a retrosynthetic problem. So propose a synthesis of the following. So what pieces do we need in order to build this? So when we're looking at our alpha position, do we really care about this alpha position? No. What we're really looking at is this alpha position, right? Oh, shoot. Sorry, this should be an H. There we go. That simplifies things. That also can't be an alpha position because it's not a carbon, it's a hydrogen. And then our beta position, is it going to be right here? That is a beta position, but we're interested exclusively in the beta position where the alcohol is coming off. So retrosynthetically, we said we know that we formed that bond, and we know that this used to be a CO bond, right? CO double bond in particular. So if we break this apart, we've got this aldehyde, and then let's take a look at that bottom part too. Are these the same or are they different? They're the exact same compound, right? So we don't even have to draw it twice unless you really want to. The reality is you just need this plus sodium hydroxide and water in order to get your aldol condensation and get to your beta hydroxy aldehyde. Does that make sense? They look way more complicated than they actually are. It's as simple as identifying those alpha and beta positions. All right, there's a variant of this reaction too called the Aldol condensation. Does anybody know what it means whenever you see the word condensation in terms of organic chemistry reaction? Loss of water. It's actually even broader than that. It's loss of any small molecule. Usually it's in reference to loss of water. So if you think about condensation on your windows, that's water building up. So in the aldol condensation, we're going to lose water from the addition product. So let's take a look at how we can do that. We'll use our acetaldehyde example. We know if we treat this with sodium hydroxide, it will deprotonate our alpha position, give us an enolate. This enolate we know can add into another equivalent of acetaldehyde and kick up electrons. Oops, sorry, this oxygen should have a negative charge. And then we've got our methyl group sticking out there. And we know with water around, we can protonate this alkoxide in order to get our final alcohol. When we do this, though, we're regenerating base. This base can do some more chemistry, right? So if we look at it, this base has some protons it can go after. It could deprotonate that alcohol and go in the reverse direction, but that's not getting us anywhere useful. But we also have some alpha protons remaining, right? So this is a weird example that breaks the rule that I told you before, where I told you before that an alcohol is a terrible leaving group. In this case, it's an acceptable leaving group. So this will clamp down and kick off our alcohol, and this acts as a leaving group. This is the only case, at least in this class, where an alcohol is an acceptable leaving group. Let me actually draw this out further over here. So we can get this product, but what do you think the other product is we might get out? Could get the cis alkene, right? So we've got our trans alkene here. We could get our cis. Which one do you think is our major product? Trans, exactly. Simply due to sterics, if we look at this, we've got this steric clash between that oxygen and this methyl group. So this will be our minor product, and this will be our major product. Like I said, this is called an aldol condensation because essentially you're kicking off hydroxide, which will protonate and form water. This reaction is highly favorable under high temperature conditions. Why do you think it's favorable under high temps? What products are normally favored under high temperature conditions? Thermodynamic products. Why is this thermodynamically favorable? Nobody's even blurting out resonance, I'm surprised.
Resonance.
Conjugation, yeah. So the more conjugated we get, the more thermodynamically stable we get. So in this case, the thermodynamic driving force is forming this conjugated alternating double, single, double bond system, right? So let's make a few notes. It forms a thermodynamically stable product, and the product is called an alpha beta unsaturated ketone or aldehyde. So the reason it's called alpha beta unsaturated is we look at our alpha carbon and our beta carbon, we've got an unsaturation point, meaning we've got a double bond, right? Pretty straightforward. And then the second note is that this reaction is favored at high temp. What's another reason we could come up with to explain why this is favored at high temperatures as opposed to the beta hydroxy product? Besides conjugation and resonance. Remember, there's enthalpy, and what's the other half of the equation? Entropy, right? So entropically, by kicking off that water molecule, we're creating more disorder, and that's another driving force behind this reaction. So high temperature, it favors an increase in entropy, right? So that's another way of thinking about it if you're struggling. All right? Pretty useful reaction, but let's make a little chart because these are closely related to one another. So we said if we've got this aldehyde and we react it with itself, we can go to our beta hydroxy aldehyde, or we can heat this up and we can get to our alpha beta unsaturated ketone plus water. So if we look at it this way, this reaction is called an aldol addition. And this is favored at moderate or low temps. However, if we want to just overshoot and go directly to our final product, we don't call it an aldol addition anymore, we just call it an aldol condensation. The key takeaway from this chapter is that enolates act as really good nucleophiles and will do all sorts of unique substitution chemistry. All right, let's take a look at another example. In all of these examples, we've used only one aldehyde, right? And the aldehyde reacts with itself. The question is, what happens if we just throw two aldehydes together? What products could we get out? And that's referred to as a crossed aldol reaction. Okay, and for this reaction, I'm going to try to color code things as best I can. For the first product, I'm going to draw it in blue. I've got this aldehyde, and for the other product, I'm going to just draw a red aldehyde. So we're mixing these two together under basic conditions and aqueous. The question is, what product will we get out, or what products will we get out? The tricky thing is, if we look at these alpha protons versus these alpha protons, they have really, really similar pKa's. So it's kind of a toss-up in terms of which one's going to get deprotonated, right? So let's just say we have the red one react with another equivalent of the red one. Let's draw that aldol product. If we do that, we can link them together. Get something that looks kind of like this, right? So we've got our beta hydroxy aldehyde, where we had two equivalents of that red starting material combined. The other option, is what if we had two blue ones combined? Okay, well, if we do that, again, we get a beta hydroxy aldehyde. It looks like this. So two of those can combine together. What's another option? Well, mix them, right? But the order of mixing actually matters in this case. So we can get two other mixed aldol products. The first one would be, let's just, for the sake of argument, have blue on the left and red on the right. That could be one crossed aldol product. Or we could have red on the left and blue on the right. So if you were just to take this reaction and stir it up willy-nilly without paying attention to order of addition or anything like that, you would end up with 4 products that would be pretty difficult to isolate from one another, right? Chemists typically avoid crossed aldol reactions like this, where they just shake things up in one flask and they let it go because of this problem. However, there are some really useful solutions to exclusively get one product over the other. So let's talk about some tricks that we can use to avoid getting this giant mixture. What's one trick we can do? Does anybody have an idea? I'll give you guys one easy answer. Don't use 2 different aldehydes, right? If it's a problem, just don't do it, right? So use only one aldehyde or ketone. That's a simple enough solution. You don't get mixed products when you're only dealing with one. Another thing you can do is really, really carefully pay attention to your order of addition. We've been using sodium hydroxide, but what if we used a much, much stronger base? What's a stronger base we could use instead of sodium hydroxide? Had that acronym? Not DBU. That's a decent guess. A really big, bulky, non-nucleophilic base. LDA, yeah. So lithium diisopropyl amide is a really good base for doing aldol reactions. So the trick that a lot of chemists do is they drip their first aldehyde or ketone the one they want to act as the nucleophile into LDA. This forms approximately 100% of your enolate, meaning you're no longer in equilibrium conditions. You've exclusively driven one aldehyde or your one starting material to its enolate. And then you take that enolate and add it into the second reagent that you're treating as an electrophile, right? So in this case, you oftentimes do what's called a cannula transfer, where you actually have 2 flasks side by side, and you essentially siphon one flask into the other flask under air-free conditions, and you can get this reaction to work quite nicely. So you first do that, then you transfer your enolate, which is your nucleophile, to your other ketone or aldehyde, which you want to be your electrophile. In this case, order of addition matters, right? So let's even make a side note of that. It's in all caps, which means I'm quite serious about that, right? It's like I'm yelling at you. All right, third one. Another easy solution is, well, let's just pick a reagent where only one of them has alpha protons. That's a simple enough solution. So let's take a look at an example of that here. So So use reagents where only one of the aldehydes or ketones has alpha protons. So let's take a look at this example. Let's say we've got this aldehyde and we've got this aldehyde. And we go ahead and we treat this with sodium hydroxide. If we look at it, this aldehyde over here doesn't have any alpha hydrogens, right? So if we were to react these two together, the only option for our base is to pluck off protons, coming off of this position. We'll form our enolate. And then this enolate can add into our benzaldehyde, kick up electrons onto the oxygen. And then last but not least, we can protonate this in order to get our neutral addition product. What's that? Sorry, thank you. I'm going too fast. One unique thing with this example is you actually cannot isolate your beta hydroxy aldehyde. Does anybody know why? We said that under certain circumstances, especially a high heat, we can drive the condensation. So let's take a look at what could happen here. So we've got more hydroxide floating around. We've got additional alpha protons. We said that we can pluck off this alpha proton, clamp down, kick off this hydroxide. Let me actually do it this way. There we go. Let's take a look at our product. Why do we get almost exclusively our condensation product? Whenever you're in doubt. Yeah, it's conjugated into a system with aromaticity, and like Ramon said, we've got a highly substituted alkene here. So there are some certain circumstances where you can exclusively get your condensation product. You can't really stop at that beta hydroxy ketone. And this is highly conjugated. So it's thermodynamically favored. All right, let's take a look at one last example reaction before we call it quits today. Let's do a retrosynthesis of this compound. What two aldehydes or what two ketones or what mixture of aldehydes and ketones would we need in order to build this? Well, the first thing we got to do is identify the alpha position and then the beta position. We take our scissors, cut that, and we say, well, this used to be our CO double bond, which means this compound on the left looked like that. The compound on the right must have been some sort of aldehyde. And in this case, it looks like we added the compound on the left into the compound on the right, which means that this should be our nucleophile, which means we need to turn into enolate. And this must be our electrophile. We can't just shake these together with sodium hydroxide, so order of addition matters. First thing we'll do, sorry, I know we're going a little over time, because we're going to treat this with LDA, right? We'll deprotonate that ketone on the left, get our enolate. Then in step 2, we'll add that into the aldehyde that we're using as our electrophile. And then step 3, we'll treat this with water to give us our final product. So that's why I was saying order of addition is super important for these reactions. All right, I think that's where we're going to end today. Next week, we'll start talking about Claisen condensations.